Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will deliver my lecture on concept of metamorphic faces. I will cover this topic under the following heads: Introduction, Concept of Metamorphic Faces. Hope it will be useful for you. Try to be regular in course. The grade of metamorphism referred to the intensity of the metamorphic event that a rock has suffered, and most commonly, the term is used to imply the maximum temperature or pressure of metamorphism. As the temperature or pressure increases on a body of rock, we say that the rock undergoes prograde metamorphism or that the grade of metamorphism increase. Metamorphic grade is a general term for describing the relative temperature and pressure conditions under which metamorphic rocks form. The changes in mineral assemblages are due to change in the temperature and pressure condition of metamorphism. Thus, the mineral assemblages that are observed must be an indication of the temperature and pressure environment that the rock was subjected to. This pressure and temperature environment is referred to as metamorphic faces. This is similar to the concept of sedimentary faces, in that a sedimentary faces is also a set of environmental conditions present during deposition. Barrow in 1853 to 1932, while mapping in the Dalendian region of the Scottish Highland, was the first person to recognize the zone of progressive metamorphism. Barrow mapped zones that were characterized by the presence of index minerals chlorite, biotite, almandine garnet, stolite, kyanite, sillimanite. The boundary between each zone was marked by the appearance of one of the index mineral in the field, which was later confirmed by the Telly, and he coined the term isograde to explain the boundary between the metamorphic zones. The type of metamorphic that give rise to this sequence of metamorphic index mineral is known as Barrovian metamorphism or intermediate pressure temperature type of metamorphism. Later, mapping in Buchan region of the eastern Dalendian revealed a sequence of progressive metamorphism which was different from Barrow zone. It was biotite, cordierite, andalusite, sillimanite. This sequence is known as Buchan metamorphism. This is also known as low pressure temperature type of metamorphism. The concept of metamorphic faces was first conceived by the Finnish petrologist Pentti Askola in 1883 to 1964, while working on the contact areoles of Finland. At the same time, Goldsmith published his work on another contact areoles of Oslo, Norway, and Askola was able to compare his result. He found that rock of same bulk composition from the two localities gave rise to different sequence of mineral assemblages as one approaches the respective intrusive. He explained this to the rock having crystallized at different pressure temperature condition and explained the two set of assemblages as belonging to different metamorphic faces. Petrologists previously considered individual mineral as index of metamorphic grade, for example, Barrow zones, while Askola recognized that it was group of minerals or metamorphic minerals assemblages which was reliable indication of pressure temperature conditions. Many definitions of metamorphic faces have been proposed in the literature. One of the recent definition is by Turner 1981. A metamorphic facies is a set of metamorphic mineral assemblages repeatedly associated in space and time such that there is a constant and therefore predictable relation between minerals composition and bulk chemical composition. A metamorphic facies as defined above is the collection of mineral assemblages from rock of all bulk composition that crystallize at the same pressure temperature condition. For example, all of the rocks collected from a single outcrop may be pylites, calcilicate or amphibolite, by definition belonging to the same metamorphic facies. Thus, we can use mineral assemblages to define pressure temperature condition. See the ACF diagram of the almandine zone of green schist facies. We can observe different mineral assemblages. Peltic assemblages, almandine, biotite, kyanite, albite, microcline, quartz. Basic assemblage, garnet, hornblende, epidote, albite. Calcareous assemblage, epidote, calcite, tremolite, actinolite plus minus quartz. The concept of metamorphic facies is that if we know the bulk composition of a rock that a PT condition at which crystallize, we can predict the mineral assemblages. Later, Gibbs published a series of papers on the thermodynamics of heterogeneous equilibria, which provide a framework for a thermodynamics treatment of the metamorphic facies concept and is the approach used extensively today by most petrologists. One implication of metamorphic facies is that if a facies is defined as a set of mineral assemblages, then there should be a different facies for each different set of mineral assemblages. Ascola originally proposed 8 facies series, and over the year new facies and subfacies were defined. Metamorphic petrology in part becomes a matter of subdividing rocks into appropriate facies. Moreover, metamorphic facies are a very convenient way to explain the metamorphic grade. I will cover this topic in 2 parts. In this lecture, I will proceed under the following heads: introduction and type of metamorphic facies. Hope it will be useful for you. Try to be regular in course. The grade of metamorphism referred to the intensity of the metamorphic event that a rock has suffered, and most commonly the term is used to imply the maximum temperature or pressure of metamorphism. As the temperature and or pressure increases on a body of rock, we say that rock undergoes prograde metamorphism or that the grade of metamorphism increases. Metamorphic grade is a general term for describing the relative temperature and pressure conditions under which metamorphic rocks form. The changes in mineral assemblages are due to change in the temperature and pressure condition of metamorphism. Thus, the mineralogical assemblages that are observed must be an indication of the temperature and pressure environment that the rock was subjected. This pressure and temperature environment is referred to as metamorphic facies. Barrow in 1853 to 1932, while mapping in the Darledian region of the Scottish Highland, was the first person to recognize the zone of progressive metamorphism. Barrow mapped zones that were characterized by the presence of index minerals, chlorite, biotite, almandine garnet, sterlite, kyanite, sylvinite. The boundary between each zone was marked by the appearance of one of the index mineral in the field, which was later confirmed by the Telly, and he coined the term isogard to explain the boundary between the metamorphic zones, the type of metamorphism that give rise to this sequence of metamorphic index mineral is known as Barrovian metamorphism or intermediate pressure temperature type of metamorphism. Later, mapping in the bookend region of the eastern Darlandian revealed a sequence of progressive metamorphism which was different from Barrow zones. It was biotite, cordierite, andalusite, sillimanite. This sequence is known as bookend metamorphism. This is also known as low pressure temperature type of metamorphism. On the basis of phase diagram of Al2SiO5 triple points, kyanite, sillimanite, andalusite after Holdaway 1971, we can show the different metamorphic phases which is summarized in table with phases name and metamorphosed mafic assemblages. Metamorphic phases, mineral assemblages of metamorphosed mafic rocks. Geolite phases, important assemblages is geolite, lomentite and analcine. Prehenite, pumpelite phases, important mineral assemblages is prehenite plus pumpelite. Blue schist phases, important assemblages glaucophin plus lawsonite, epidote plus minus albite and plus minus chlorite. Eclogite phases, important assemblage is omphacite, pyroxene plus garnet. Green schist phases, chlorite plus tremolite or actinolite, epidote plus minus albite. Epidote amphibolite phases, plagioclase, the variety varies from albite to oligoclase plus hornblende plus epidote. Amphibolite phases, plagioclase, oligoclase to andesine variety, hornblende plus garnet. Gamulite phases, orthopyroxene, clinopyroxene, garnet plus plagioclase. There are few points which are significant with respect to metamorphic phases concept. First point, metamorphic phases are defined by the mineral assemblages that observed in mafic rocks. Each phases that is different bulk composition will have different mineral assemblages. For example, if we see the ACF diagram of garnet zone of green schist phases at 500 degree centigrade and 5 kilobar pressure, one can observe the following assemblages. Peltic schist have the assemblages kyanite plus garnet plus muscovite plus quartz. Basic rocks contain hornblende, plagioclase, epidote, garnet, chlorite, etc. And calcite contain calcite, epidote plus tremolite. Second, the boundaries between different metamorphic phases represent the pressure temperature condition where chemical reaction take place. In metabasaltic rocks, important new minerals form or break down. For example, the boundary between green schist and amphibolite phases, the epidote plus chlorite plus tremolite, which is important assemblages of green schist phases, react and form amphiboles, though which represent amphibolite phases, derive its name. See the ACF diagram of green schist phases and amphibolite phases. Similarly, the boundary between amphibolite and gamulite phases where amphiboles break down to form pyroxene. Third, phases boundaries are not absolute boundaries but zones, which is shown in figure and summarized. This is because the iso guard separating the phases occur at certain pressure temperature which are sensitive to the bulk composition. Fourth, phases boundaries depend not only on the temperature but also on the lithostatic pressure and P water as well. If P S2 is decreasing PS2O relative to P total, PS2 less than P total, resulting in lowering the temperature of faces boundaries. For example, experiments on the amphibolite to gamma-lite faces transition conducted with PS2 equal to P total at nearly 800 to 850 degrees centigrade. Fifth, the faces to which is observed by a rock always show peak metamorphic condition. The PT path is of considerable more important in the interpretation of processes than is the metamorphic faces by itself. Dear student, today in this lecture we have discussed about the type of metamorphic faces. I have covered this topic under the following heads: Introduction, Type of Metamorphic Faces. I believe this lecture was useful for you. In my next lecture, I will cover classification of metamorphic faces. For further studies, please read the textbooks, references and links given in the text.